Jai Hind to all, welcome back. My name is Vaishali Deshwal and currently I'm working as an assistant professor at AKGEC Ghaziabad. So this is the MLT session, Machine Learning Techniques, and the code for this subject is BCS 055. So in today's lecture, we'll cover these topics like Bayes optimal classifier, then Gibbs algorithm, naive Bayes classifier, and Bayesian belief network or BBN. So all these concepts, they are related to Bayes theorem. We have already covered what is Bayes theorem, what is a formula for Bayes theorem, and what is conditional independency between the events. Now let's start with the Bayes optimal classifier. Let's start with the Bayes optimal classifier. So till now we are focusing on identification of the most probable hypothesis given the training data. So we are given training data and we are interested in finding out the most probable hypothesis. But now our target shifts to find out the most probable classification of the new instance. So if I have a new instance denoted as X, so I'm interested in finding out the most probable classification of it. Let's say if I have two categories, one is yes, the other one is no. So I'm interested in finding out that whether this instance belongs to yes category or it belongs to no category. So till now we have studied that this can be answered by simply applying the map hypothesis, that is maximum a posteriori hypothesis. In this we have to maximize the probability and finding out the posterior probability. So by applying the map hypothesis to new instances, we are able to answer that what will be the most probable classification of the new instance. And in fact, it is possible to do it in a better way. So let's take an example here. To develop some intuitions, consider three hypotheses. So we are having a hypothesis space here, that is capital H, and I am having three hypotheses, H2, H1 and H3. H1 value is 0.4, H2 value is 0.3, H3 value is 0.3. So these are the values, or you can say posterior probabilities of these hypotheses, 0.4, 0.3 and 0.3. So H1 is your map hypothesis as it is visible from these values because the value is 0.4 for H1. So here it is the map hypothesis and there is a new instance, let's say it is denoted by this X. So it is encountered now and which is classified positive by H1. So it is positive, this new instance is positively classified by H1 and negatively classified by H2 and H3. So taking all the hypotheses into the account, the probability that X is positive is 0.4. Obviously, it will be 0.4 only, but the probability that X is negative, it will be 0.6. Why? Because H2 and H3 classifying it as negative, and when we add 0.3 plus 0.3, then we get 0.6. So now we have a contradiction here. The most probable classification, that is the negative, that is 0.6 in this case, is quite different what we are getting from the most map hypothesis, that is maximum or posteriori hypothesis. Okay. So now in general, the most probable classification of the new instance, now we are talking about the Bayes optimal classifier. In Bayes optimal classifier, it says the most probable classification of the new instance is obtained by combining the predictions of all hypotheses weighted by the posterior probabilities. As you can see from this formula, we are interested in finding out when D is encountered, or you can say D has already occurred. We have the data set already, we have seen the data set, and we are interested in finding out the values Vj from some set V. Suppose if I am having two categories, yes or no, so V can be yes or V can be no. So these are the values. Now if we expand the formula according to Bayes optimal classifier, then it is by combining the predictions of all hypotheses. We are combining the predictions of all hypotheses weighted by their posterior probabilities. So we are interested in the posterior probabilities, and we are just multiplying these two terms. So this is the Bayes optimal classifier. Anything which can be classified with the help of this equation or this formula, it is the Bayes optimal classifier. So if the possible classification of the new example can take on any value Vj, so Vj can be like, it can be yes or it can be no. If we have two classification, or if we are dealing with the binary classification here, then the probability, that is Vj by d, that the correct classification for the new instances Vj is given by this particular formula. So the optimal classification of the new instance is the value Vj, for which you have to maximize this particular value, that is P Vj by t. D is your data set and V is your values from some set capital V. So now this is the equation of Bayes optimal classification. We have already studied it. We have to maximize this particular value. That is why we are using a mathematical function, that is argmax. So argmax Vj belongs to capital V. This is the value. It belongs to capital V, all the values. And summation hypothesis belongs to the hypothesis space. We are representing hypothesis space with this capital H. So it can contain many hypotheses, individual hypotheses H1, H2 and so on. Then we have the combination of the probabilities weighted by their posterior probabilities. So anything which can be classified with the help of this equation, it is by the Bayes optimal classification. Now we'll see an example or we'll discuss this concept, the Bayes optimal classifier, with the help of an example. So in this example, as you can see, we are having a new instance and V values. V is plus and negative. So we have two classes here, one is positive and one is negative. We are given some data set here, like P H1 by D is equal to 0.4, P minus H1 is equal to 0, and when H1 hypothesis there, then what will be the probability of plus, that it will belong or it will associate with the positive class. So it will be 1 only. Okay, so such data set is given to us. Now we have to apply the Bayes optimal classification in this and find out the classification, that to which your new instance will belong, whether it will belong to this positive class or it will belong to your negative class. So simply applying this formula, as we have studied here, Vj, so we'll apply in the place of Vj, we have to expand the formula for the positive class in one go, and in the second go we have to apply the same formula for the negative class. So here positive H1, P, H1 and D. So we have to expand this formula for every data point, like H1, H2 and H3. So if I expand this formula, it will be like positive by H1 dot positive H1 by D. So it will be for H1. Now you have to write same thing for the H2, then H2 dot probability H2 by D plus probability positive by H3 dot probability of H3 by D. Okay, so here we have the values, like positive H1 we have 1, and then H1 by D we have 0.4. Similarly 0.3 plus 0.3. So on multiplication you get 0.4 as your answer. So it is 0.4. So here we are getting 0.4, and similarly you will expand this formula also for H1, for H2 and H3. Simply you will put the values given in the data set and we get 0.6. So 0.6 is obviously greater than from 0.4, and with the help of this we can say that your new instance will belong to the negative category. Okay. Now any system that classify the new instance according to 6.18 equation, that is nothing but this equation. So it is your Bayes optimal classifier or Bayes optimal learner, you can say. Now no other classification can outperform this method. It gives you impeccable results. So no other classification method using the same hypothesis space and prior knowledge can give you or can outperform this particular method. But there is some limitation or disadvantage of this method, and we'll discuss that disadvantage later on. Now, this method maximizes the probability that the new instance is classified correctly, and given the available data, hypothesis space, prior probabilities over the hypothesis. Means it maximizes the probability that the new instance is correctly classified, that whether it belongs to the yes class or no class. So it ensures that it maximizes the probability of the exact classification. Okay, so we are done with the Bayes optimal classifier. Now I'll discuss the limitation of the Bayes optimal classifier, and that can be resolved with the help of Gibbs algorithm. So although the Bayes optimal classifier outperforms all other methods and it obtains the best performance that can be achieved from the given training data set, but it is quite expensive to apply. And why it is expensive? What is the logic? The logic is that it computes the posterior probability for every hypothesis. If you have 100 hypotheses, 1000 hypotheses, or many hypotheses in your hypothesis space, then you will calculate or compute the posterior probability for individual hypothesis. And that is why we are saying that Bayes optimal classifier is quite expensive. Then combines the prediction of each hypothesis to classify each new instance. So it is quite expensive, and we can overcome this disadvantage by having another algorithm that is known as Gibbs algorithm. So it's an alternative, and it is quite less optimal in comparison to the Bayes optimal classifier. And here we are having the reasons. So this is the algorithm, how we are going to perform Gibbs algorithm. So the first point is that we have to choose the hypothesis H, individual hypothesis from this capital H at a random and according to the posterior probability distribution. Okay, so as we have discussed earlier, we have discussed an example in that we are having three hypotheses and the values were 0.4, 0.3, 0.3. So one is 0.4, other one is 0.3 and 0.3. So here H1 has the high posterior probability. So according to the Gibbs algorithm, we will choose this hypothesis. So second point is use this H hypothesis to predict the classification of the next instance, means X. Okay, so this is a simple algorithm, involves two steps only. And this is the limitation of this algorithm, that the expected value of the error of Gibbs algorithm is at worst twice the expected value of the error of the Bayes optimal classifier. Fine. So I hope you are clear with the Bayes optimal classifier and the Gibbs algorithm. Moving on to the next topic, we have naive Bayes classifier. So here we have a term, a next term called naive, and this is what it makes it different from the Bayes optimal classifier. So naive Bayes classifier considers an assumption that all the events, they are independent among the features. So this is the formula. It says PA by B is equal to PB by A dot PA by PB. So we have discussed this formula in the last lecture. You can see that. A classification technique. So it's a classifier. So it's a classification technique, and mainly it is used for the classification purpose. So it is based on the Bayes theorem. We have the formula, the same formula as we have used in the Bayes theorem, with an assumption that all the features or all the events, they are quite independent. Okay, so moving on, now I'll discuss this topic with the help of an example, that how we can solve the numericals based on this naive Bayes classifier. So here we have some features. The features are yellow, sweet and long, and we have some fruits, orange, banana, others. So there are the features again, yellow, sweet and long, and the values are given to you, data set is given to you. Question is, among these fruits, which one has the highest probability of being yellow, sweet and long? So you have to apply the naive Bayes classification or Bayes theorem. So here we apply the Bayes theorem It says P yellow by orange. So the logic is you are interested in finding out that whether the orange or banana or other fruit has orange, banana or the other fruit, which fruit has the most or higher probability of being yellow, sweet and long. So we apply the formula or the Bayes theorem. The theorem says if the fruit is orange, how will you expand this? P, what is the probability if it is orange, then it will be yellow, then orange, it will be sweet dot or multiplication long orange. So you will find these values: probability by yellow, yellow by orange, probability of sweet by orange, probability of long by orange. So if I expand this formula or applying the Bayes theorem to it, I got PO by y dot PY divided by P orange, and this is what we are calculating here. So we will expand this formula P yellow by orange by applying the Bayes theorem. Simply put the values. For example, P orange by yellow. So total yellow is 800. Total fruits which are yellow is 800. And you're interested how many yellow oranges you have. So yellow oranges are 350. So the probability will be 350 by 800. P yellow are 800 and total fruits are 1200. So 800 by 1200. P orange is 350 and it will be divided by, so total orange are 650 and total fruits are 1200. So 650 by 1200. Simply put the values of probabilities and compute, and then we'll get 0.53. In the similar fashion, we'll calculate all these values. For example, we will calculate PS by O, then P long by orange. So here the value is 0 and here the value is 0. It is not, okay, so it is 0.69 and it is 0. You will multiply all these values and you'll get 0 answer. So second step, you will repeat the same steps for banana fruit and for the third category, that will be the other. So from or after the computation, the conclusion is that the maximum probability is for banana. So banana will be the answer, or banana has the highest probability that of being a yellow in color and long in size and sweet in flavor. Okay, so now this is the last topic of our lecture today, that is the Bayesian belief networks. Bayesian belief networks, as it is a network, so it's a probabilistic graphical model that represents the conditional dependencies between the random variables, and there are some concepts related to it. So here it is a probabilistic graphical model and it represents some conditional dependencies also. So it represents the probabilistic dependencies between two events or more than two events, and we have some concepts. Main two concepts are these. First is the DAG, that is the directed acyclic graph, and second is your conditional probability table, that is CPT. So the graphical, what is DAG? In DAG you will have some nodes, and in those nodes you will have some edges. Between these nodes you will have some edges. So it's a graphical structure where the nodes represents random hypothesis and edges indicates the probabilistic representation without cycles. So cycles should not be there. Okay, so these are your hypotheses, and these edges, they represent some probabilistic relations without any cycle. Now you have the other concept that is called CPT, that is the conditional probability table. So it defines the probability of each variable given its parents variable in DAG. Let's take an example to understand these concepts. Each node is a hypothesis or a random variable. Here I am taking this particular example, that if it rains then dog will bark, and if dog bark then cat hides. So here the example for the dog bark hypothesis is the two probabilities. that if it rains, that dog may bark or may not bark. So in this manner, you will represent the CPT or your not CPT, it's DAG. You have some notes and you have some edges to represent the relationship between those hypotheses and between those notes. Next is the CPT, that is the conditional probability table. So as you can see in the first place, it is the first row and the first column. It says that when B is equal to true and R is also true, means if it rains, then what is the probability that dog will bark? So it is 9 by 48. And when it is not raining, then what is the probability that dog will bark? That is 10.48. So in this manner, you can calculate the probability calculation. That is P, probability that P is true and R is T, true, that is 0.19. And what is the probability that B is true and R is false? Means if it is not raining, that is 0.375. So this is about the CPT, conditional probability table. Okay. Now this is the Bayesian network example. We have taken an example here, and this is the dependency. So if burglary is true and earthquake is true, then alarm will ring, and if alarm rings, then P1 will call or P2 will call. So this is the dependency, and alarm depends on the burglary and earthquake. P1 and P2 depends on alarm. So as you can see the explanation also, that the Bayesian network shows probabilistic relationship. Burglary and earthquake can trigger the alarm, and if alarm rings, then it may cause P1 or P2 to call. It may cause, okay. So DAG, directed acyclic graphs, they're useful for modeling such kind of dependencies, as we can easily see the dependencies between these events. Okay, so this is the data which is given. The given probabilities are that if burglary is true, what is the probability that burglary is true? That is 0.001. If burglary is false, then it is 0.999. Okay, that is 1 minus when the probability is equal to 2. Now we have the conditional probability table. It says that if burglary is true and earthquake is true, then what is the probability that alarm will ring? So alarm will ring is 0.95, and if it doesn't ring, then 0.05. Okay. Now if alarm rings, then what is the probability that P1 will call? That is 0.90, and if it doesn't call, then 0.10. So the data set is given to you. Similarly for the P2. So here we have an example, and the example is that find the probability of P1 is equal to true, P2 is equal to true, A is true, B is false, and E is false. So find the probability of this thing, and this is given to you, and the data is given to you. So we already know P1 and P2 depends on alarm. Alarm depends on B and E, and B and E, they don't depend on anyone, on any other event. So P1 by A, because P1 depends on A, then P2 by A, then P, A, not B and E, because it is given that B and E is false in this particular example. That is why we are taking not B and not E. Then not of B probability and probability of not E. And in this formula, you'll put the values which are given to you in the question. For example, P, probability of P1 and A. So alarm rings. So if alarm rings, then P1 is true, it is 0.90. So the value is 0.90. P2 and A means alarm rings and P2 is also true. So the value will be 0.70. So in this manner, you have to calculate you have to do the calculation in such type of questions. Apply the concept of Bayesian network and prepare your CPT table. Data is given to you. Simply put the values and your answer will be 0.0062. So this is it for today. We have completed all the concepts related to the Bayes theorem. In the last lecture, we have discussed what is Bayes theorem. You can watch that. In this lecture, we have discussed some important topics related to the Bayes theorem, like naive Bayes classifier and Bayes optimal classifier, etc. We have done one numerical related to the concept. So in the next lecture, we'll discuss unit 3 of MLT, that is decision tree algorithm. and ID3 algorithm based on decision tree and the numerical also. So thank you.